Welcome to solverfy.
For this question, I'm going to use conservation of energy and conservation of angular momentum. So, m r initial times v initial, because r initial is perpendicular to the v initial, equals m r final times v final. Again, we're going to take them to be perpendicular to each other. The masses cancel out. And we get the initial radius is 3r, or is perpendicular to the velocity. It's 3r sub e times vi. And this one, perpendicular to the velocity, is going to be just r sub e, because it's just barely going to pass the surface of the Earth. The r sub e's cancel out. And now we can see that Vf is 3 times Vi. Now, conservation of energy. Kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. 1/2 m V initial squared. The potential energy, since it's far away, we're going to set that to 0. 1/2 m V final squared minus g m over r sub e, because again, at the end, it's going to barely pass the surface of the Earth. All of the m's cancel out, and we can substitute 3vi for Vf. So let's continue. 1/2 Vi squared equals 1/2 Vf squared minus Gm over Re. So again, Vf is 3 Vi. Okay, rearranging, we can get 1/2 of 3 Vi squared minus 1/2 of Vi squared equals Gm over R sub E. So factoring out the 1/2, 3 Vi squared is going to be 9 Vi squared minus Vi squared equals Gm over R sub E. Multiplying by 2 on both sides, this side becomes 2Gm over R sub E. And the other side becomes 9Vi minus 1 Vi is 8 Vi squared. Now I'm going to divide by 8 on both sides, and I'm going to get Vi squared is Gm over 4Re. And finally, Vi is the square root of Gm over 4R sub E. So the keys to this one are using conservation of angular momentum and realizing that the final is going to barely pass the surface of the Earth.